Welcome everyone to this week's Autonomy Talk. This week is a great pleasure to have with us Professor Pratap Tokekar, who is an associate professor in the Department of Computer Science at the University of Maryland. So some short bio for Pratap. He obtained a Bachelor of Technology degree in Electronics and Telecommunications from the College of Engineering in Pune, India. He then got his PhD in Computer Science from the University of Minnesota in 2014. It then was briefly a postdoc at the GRASP Lab at the University of Pennsylvania. And also between 2015 and 2019, he was an assistant professor at Virginia Tech. As you can see from his bio, he's won a number of awards, and his work has been recognized by some interesting recognitions, for instance, the Amazon Research Award or the NSF Career. And today's talk is going to be about leveraging learning and optimization-based planning for multi-robot systems. This is an exciting area that's growing, and we're very excited to hear more about it in this seminar series. And therefore, I give you the stage. Pratap, go ahead. The stage is yours.
Awesome. Thanks a lot, Jale. This is really is a pleasure and an honor to be speaking in the seminar series. I've been following the seminar series for a while. I think it's a great initiative, and I'm glad that it has continued beyond sort of the pandemic. I think this is a great way of connecting researchers across the world and sort of have people share their exciting work. Um, I'm sort of glad that I have this opportunity to talk about some of the stuff that my group has been doing over the past few years. I'm part of the computer science department, but I'm also part of the Maryland Robotics Center here at University of Maryland. Uh, sort of Before I get into the technical portion, I want to acknowledge that everything that I'll talk about is basically work done by my students and postdocs who work with me. So here they are, and I'll acknowledge them along the way. And then you'll also see some of the robots that have been helping us doing the research over here. So more broadly, my group is interested in answering this question. So how do you take a team of heterogeneous robots and plan and coordinate their actions so as to gather interesting data from the wild? So in my group, we sort of wear two hats. So we have our algorithmic hat, where we try to design multi-robot coordination and planning algorithms, and increasingly multi-robot reinforcement learning algorithms for getting robots to coordinate with each other in a variety of scenarios under a variety of constraints. And that's what I want to talk about today. But then we also have the other hat that we wear, where we not only sort of design algorithms, but we actually build systems and deploy them out in the real world for a number of data collection applications. So things like environmental monitoring, where we are using a team of aerial robots along with robotic boats to gather data from water bodies to sense the water quality, sense if there are chemicals that are being released, how they are transported in the air, and so on. We've been working in agriculture using, again, air and ground robots, and I'll talk a little bit more about this. Again, for assessing basically the health of your crops using actual data that's collected by these robots. And then we've been looking at infrastructure inspection using UAVs to fly close to infrastructure with high resolution cameras to look for sort of visual defects like cracks, corrosion, rust, etc., so that we can take preventative measures in time. So we have sort of two things that we do in my lab: design algorithms, but also deploy them on hardware for in support of these applications. In this talk today, I'm going to focus more on some of the algorithmic work that we are doing. In particular, I want to focus on sort of a narrow slice of work that involves learning and planning and finding ways of sort of both doing learning and planning simultaneously. And to set this up, sort of I have this tweet from Subbarao, and I sort of like this tweet because it's sort of tongue-in-cheek in a way, where he says planning and reinforcement learning are two central areas of AI that are separated by a common problem. It's sort of tongue-in-cheek in the sense that a lot of what we do in RL actually can be done with planning, and there's a lot of sort of planning work that we do actually can be done with RL or can support RL. And so these are sort of two areas that are trying to solve the same problem or similar problems in the sense, but have sort of diverged in a way and have been working in its own silos. And there is a need to do planning and RL together in some sense. And that's what I want to talk about today, which is some of the work that we've been doing in my group on using planning to improve RL. And when I mean by planning over here is optimization-based planning to improve learning. And then using learning to improve planning. And the hope here is by doing that, we'll try to bring these two central areas of AI together and sort of hopefully get the best of both worlds. So my talk is sort of split into two halves. In the first half, I'm going to focus on how we can use planning to improve learning, specifically improve reinforcement learning. And in the second half, I'll talk about how we can mix in some learning with planning. Right? Feel free to interrupt me at any point. If you have questions, you can put them in the chat or sort of feel free to speak out and ask questions along the way. Happy to make this as interactive as possible. Right? So I'm going to start with the first part, which is how we can use planning to improve learning, right? Specifically reinforcement learning. So sort of, hopefully this audience is very familiar with reinforcement learning, but just to set this up, it's a standard RL loop. We have an agent that's taking actions in the environment. We get to observe some reward and the new state after the agent takes that action. And then what we want to do is to learn the policy uh, so as to maximize the total reward that's collected. There's a lot of work that's being done on RL, including a lot of work on RL for robotics. And a natural question to ask is, is there even a need to improve reinforcement learning? In this case, what role does planning have to improve reinforcement learning? So there's some outstanding issues with reinforcement learning, especially when they're applied to a robotic setting. Sort of safety is one of the major challenges with deploying any learned controller on a robot. But then you also have to worry about generalizability, right? What if your environment that you are operating in changes? Can you still guarantee that the policy that you've learned would still be effective and safe in this new environment? Scalability is an issue, and this is something that I want to talk about today, since we're going to focus on multi-agent coordination. If the number of agent is large, or if the number of agent changes, can I still use RL in a scalable way to come up with policies for a multi-agent coordination? And then reward, right? Alignment with reward. So a lot of success of reinforcement learning in some sense is dependent on the reward function that you use. And oftentimes there is a misalignment between what we actually want the agents to learn versus what the agent ends up learning due to the reward function. There's a sort of famous example of reward hacking. There's several such examples of misalignment. A very simple example where this is the half cheetah environment in Mijoko. It's a simulated robot, but there's several examples in real world as well, where the goal really is for this half cheetah to traverse as fast as possible to the right, and to learn a policy to do that. And it ends up learning a policy like this, which is optimal in the sense of the reward function that's specified, which is sort of just move without crashing as quickly as possible to the right. But what it ends up doing is essentially breaking the simulator because it's learning for the half cheetah to start to do cartwheels over here. So you can see it's sort of rolling over, which is physically infeasible, but the simulator allows it because it sort of runs into some numerical issues, and this is the policy that you end up learning over here. Right? So this is an example of reward hacking where what we want the agent to do is not what the agent ends up learning, even if the learned policy is actually optimal for the reward function. Right? So natural question here to ask is how do we reduce the misalignment between the intended behavior and the learned behavior? Right? So one sort of common way of doing this is to use demonstrations. So here's, for example, is some work that we've been doing on assistive feeding, so using a robot arm to learn to pick up food items, acquire food items from a bowl, and use that to help feed people who are unable to eat by themselves. And a part of this is how do you acquire food items from the bowl, especially if you're sort of dealing with the diversity of food items that may be there. So you can see the robot has a camera on board that it can use to see what's actually on the food bowl. And how do we train this is through demonstrations. So we do kinesthetic demonstrations. So you hear one of my students actually moving the bowl, moving the arm, and collecting demonstrations showing how to pick up food items from the bowl. And then using these demonstrations, we learn a policy. And we can sort of also show that this generalizes to unseen food items for unseen configurations, and there's sort of more things in here to add robustness to it, right? But here's an example where we are not using a reward function, but we're just presenting demonstrations and then learning to generalize from these demonstrations. And you can sort of see the policy here. Uh, if you look at this example with the tofu, it's learning these high-level primitives where it's first aligning the tofu and then scooping it up by using the side of the bowl as guide to help lift it over here, right? And so these are all policies that are learned using demonstrations. And this works pretty well for single agent systems or for limited number of agents. But more broadly, if you want to use demonstrations for large teams of robots, you run into the scalability issue, right? So let's say you have a team of 20 robots that you want to use to perform some coordinated task. Uh, if you want to use any of these learning from demonstration, imitation learning types of methods, you would need demonstration data with 20 robots, right? You would, and then you would need sort of learn the policy from that. This is not very scalable, and this is not scalable if you expect the number of robots to change. So you sort of don't know if you're actually going to have 20 robots or not. And this is not scalable if the number of robots themselves is pretty large. And certainly not scalable if you want to collect demonstrations using those robots and not just in simulation, right? And so that's the first piece of problem that I want to focus on today. And again, I want to go back to the original motivation, which is how can we use planning in this setting to improve the learning process? So we're still going to do reinforcement learning. And in this sense, we are still going to do learning from demonstrations. But can we use planning where perhaps we have more scalable methods and then use that to improve the scalability of some of these multi-agent reinforcement learning algorithms. So before I go into some of the technical specifics, any quick questions?
Yes, Subrata, you have your hand up. Feel free to ask.
Yeah. Professor, have you tested the defects on the wind turbine blades?
We have not. That certainly is an application. So we've been focusing more on bridge inspection. And so most of the data that we've collected is for bridges and looking at cracks and mostly cracks, but potentially other types of visually identifiable defects for bridges. I would expect sort of similar performance if we are looking at cracks or other visually identifiable defects for wind turbines, but that certainly would be a great application to test things on.
Yeah, Professor, why I'm making this point is that because I happen to come from that field, and a lot of fleets are aging in US around, and not many agencies do that sort of a critical check.
Yes.
So that would be a great avenue for you, as you rightly said. And the second point which I wanted to ask you is, do you also do the soil testing apart from in the agri-tech field? The applications, as you were telling in your the first slides. Do you do the soil testing, or it's a plain agricultural mapping or quality? If you could kindly explain a bit.
Sure. So we haven't done any work with soil testing, but that's most of our work is focused on sort of non-contact based sensing. So sort of looking at multispectral imagery, for example, to identify nutrient defects like nitrogen defects, identifying NVVI and other sort of vegetation indices. Would love to do soil testing. Would love to be able to use soil probes or sort of to collect physical samples. It's something that we haven't done. And I'm
Okay,
happy to chat about sort of both of these things offline. I think, especially
great.
working in this area, would love to connect offline and talk more about these.
Yes, and also quickly, the last one is that since you are consulting on non-contact type of applications in your algorithms mainly, but do you also have a plan, or you've already done, for example, the greenhouse gas accumulation testing, or the methane gas, which is very much rife these days because there are city gas services and in the petrochemical complexes or whatever it is?
Yeah, so we haven't looked at gas concentrations, but we have looked at particulate matter concentrations. So that's for a different sort of application. But sort of some of the ideas that we have on planning and autonomy for data collection that works for particulate matter, I suspect would also work for gaseous concentration and perhaps source identification. So looking at leaks with methane and other sort of things.
Thank you. Thank you very much.
Awesome. All right. So going back here, what I want to talk about next is how we can use planning to improve the efficiency or scalability of multi-agent reinforcement learning. Uh, and the idea here is we are going to use demonstrations to learn a policy for our multi-agent team. But since we want scalability and we don't expect to get demonstrations for large number of robots, what we are instead going to do is we are going to collect demonstrations for a subset of robots or a smaller number of robots, right? And in the most extreme scenario, I'm going to collect demonstrations for single robots or one set of demonstrations for one type of robot that I may have. So for example, if I have 10 aerial and 20 ground robots, I'm going to collect demonstrations, one set of demonstrations for just aerial robots, one set of demonstrations just for ground robots. And then I want to use that to learn a policy for the entirety. And so the way we are going to do this is we are going to set up a simpler surrogate instance of the problem that we can solve using classical planning methods. You can also use humans to provide demonstrations in the simpler setting. And then we're going to use these suboptimal demonstrations, but demonstrations that still contain useful signals, and then learn a coordinated policy using these demonstrations. This is what we call as personalized demonstrations, because they have been sort of personalized for specific robots in the environment. And we want to learn a cooperative policy using these personalized demonstrations. So most of the work on this is actually done by one of my students, Pihong Yu, who is also on the call. So if you have specific technical questions, I think he'll be happy to answer. But let me sort of give you an overview of what we are doing over here, right? So this is joint learning from demonstrations. Let's say you have sort of two robots, a blue and a green robot. What you would normally do is you would collect demonstrations with these two robots operating in the environment, and then you would learn a policy for them. But now if the agent configuration changes, so for example, if I have more robots over here, I need to collect a new set of demonstrations and then learn a policy for this new configuration of robots. And if I have more robots, again, I have to collect new demonstrations. Instead, what we ask is, what if I collect personalized demonstrations, meaning that I'm going to collect only demonstrations for each agent working by themselves, right? So there's no cooperation that's involved in the demonstration that I'm collecting. So I only have, let's say, demonstrations collected for the blue robot and the green robot operating just by themselves. Can I use these demonstrations and then learn a cooperative policy using that? Right? Of course, the challenge here is that the demonstrations don't contain any cooperation between the agents, and so they are by definition suboptimal over here, but they still contain some useful information that we should be able to bootstrap. And where planning can come in over here is for these simpler instances where you just have single robot that's operating. you can collect demonstrations using sort of classical planning, right? Because this is a much smaller problem or a surrogate instance that you are solving. So that's the challenge that we want to solve. How do you learn to cooperate using these personalized demonstrations? Since they are suboptimal, we can't sort of use standard learning from demonstration techniques. So we want to sort of use them to bootstrap without resorting to, for example, behavioral flow. So I'm going to use this example as my running example over here. So this is a setup with two agents, a red agent and a green agent. The goal for the red agent is to get to this red square over here. The green agent sort of essentially acts as um, uh, a support agent for the red agent. What the green agent can do is it can get to this green square, and if the green agent is on the green square, then this door opens. And if this door is open, then the red agent can pass through it and then eventually find its way to the red goal over here, right? So in this simple setup, the red and the green agent need to cooperate with each other for them to be able to solve the task, which is for the red agent to get to its goal. Right? And the cooperation involves the green agent knowing that it has to go here and stay here to keep the door open. And then once the red agent is in the square, the green agent needs to get out of the way to let the red agent pass. So this is some cooperation that needs to happen. But what we are going to do instead is we are going to provide demonstrations for the two agents in isolation. So we are going to provide demonstrations only for the red agent. And these demonstrations are with the door open. So the red agent is sort of just learning to directly go to its goal. And for the green agent to just go to the green square over here. Right? And so we are sort of providing these demonstrations where no cooperating behaviors are demonstrated. And what we want to do is to learn a policy that learns to cooperate using these personalized demonstrations over here. So it sort of learns to use this to bootstrap learning of a policy that does involve cooperation. So this is for a specific setup, but of course the algorithm that we have is a general algorithm that works for any number of agents that may require cooperation with each other. Right. So specifically how we solve this, we call this as personalized expert guided MARL, like MARL. And I'm going to skip some of the technical details, but just to give you a flavor, this is sort of what the objective ends up looking like. So the first term in the objective is essentially the collaborative reward that you get for the team as a whole solving the task. So this can be a spark reward, for example, where the red agent reaches the goal, you get a non-zero reward and a zero otherwise. The second term here is a term that tells you how close are you to the individual demonstration. So this is for each agent, and it's looking at the state occupancy measures, and it's telling you this is the state action occupancy measure for the learned policy, and these are the state action occupancy measures for the individual demonstrations, and we are looking at the Jensen divergence between these two, telling you how closely are you matching the demonstration. And the theta is sort of a term that tells you how much we want to weigh one thing over the other, right? And so if you optimize this objective function, you will sort of try to maximize the collective reward while also ensuring that your learned policy is close to the expert demonstration. Of course, the challenge here is you don't want the second term to be operational everywhere, right? Because if you, for example, in the extreme case, eta is much larger, then you will just learn to clone the individual demonstrations that were provided. And we know that those demonstrations are suboptimal, right? So you don't just want to match your occupancy measures in for the demonstrations. What you want to do really is to use that only when you know that the conditions that you are operating in are similar to what they were during the demonstration. So specifically, if I go back to this example over here, if for the red agent operating in this part of the state space, you want to use your demonstrations because this is the part of your state action space where you don't need to cooperate with any of the other agents. And so this is where you want to sort of give a higher weight to the second term. But when you get close to the second agent, this is where you need to cooperate with the other agent. This is where you want to only rely on your collaborative reward and sort of do RL instead of learning from demonstration, because this is where you don't expect your demonstrations to match with each other. And so what we want to do is we want the second term to be enforced only in parts of your transition dynamics, only in the part of your state action space where the transition dynamics are going to be similar to that of the demonstrations. Otherwise, we want the second term to be inactive. Uh, so the way we address this, the way we solve this is by training two discriminators. So the first one we call as the behavior discriminator. The second one is the dynamics discriminator. The behavior discriminator essentially takes in a state action pair for every agent and tells you whether the chosen action is similar to the demonstrations or not. Right? And so this is acting, this is essentially telling you, are you imitating the demonstration? And this is sort of standard imitation learning framework that uses discriminators. The second discriminator is sort of the novel contribution that we have, which we call as the personalized dynamic discriminator. And this one takes in a state action next state tuple and tells you whether the current transition is similar to the demonstration or not. And then what you do is you sort of, your reward function over here, the first term is your collaborative reward. And the second term essentially is going to be based on the what your dynamics discriminator tells you. If your dynamic discriminator tells you that your transition is similar to the demonstration, then the second term is going to be active and you are going to try to imitate what the demonstrations are doing. But if your dynamics discriminator tells you that this transition is dissimilar from what we've seen, then the second term is going to be inactive and you're going to try to only optimize the first term over here. So this is sort of trying to combine your suboptimal demonstrations in parts where you think they are useful and ignoring them in parts where they are not. And we found that this works pretty well. So here's an example. Here's the results for the same example that I was using. The background color in the two figures on the bottom essentially reflect how often the agent ended up in those states during the training process. And you'll see that our algorithm, the red and the green agent, end up mostly exploring the part of your state space that are useful. Whereas if you just if you just use a standard multi-agent RL algorithm like MOPPO, there's no it's not using any prior information, so the agents end up sort of exploring sort of generally over the state action space. Whereas with our algorithm, the exploration is more directed around the part of your state action space where you expect your actual sort of trajectory to be. Right? So there's sort of more focused exploration, and that's coming in from the guidance from the personalized administration. So we have several empirical results showing that it performs better than pure MARL, pure imitation learning, or other reward shaping methods sort of for what we call as easy and hard instances. So in all cases, we end up sort of doing better than pure MARL or pure imitation learning. We sort of also seen that it works better than baselines. Here, sort of we are showing it only for 4 agents, but we have sort of more results with larger number of agents. Again, sort of scaling up much better than the baselines. And then more interestingly, we also show that this ends up sort of solves this bootstrapping, or it does the bootstrapping that I sort of mentioned earlier, which is we end up sort of performing better than the baseline. So in this specific setup, we use the StarCraft multi-agent challenge benchmark. This is a bunch of agents playing against each other. The demonstrations were collected from a policy, a simple policy that was trained sort of purely from RL, but that's trained for a few instances. And then we use that as, we roll out that policy and use those as demonstrations to then train a policy on top of. And so the demonstrations basically had a win rate of around 30%. whereas our policy ends up sort of with a win rate sort of closer to 50% over here. So it's sort of improving upon the base, the demonstrations, showing that even if your demonstrations are suboptimal, what this ends up doing is sort of learns to improve over the suboptimal demonstrations over here. In this setup, the demonstrations came from a sort of, another RL algorithm, but you could also have demonstrations coming in from a classical planning algorithm that's solving a surrogate instance. The idea is, even if your demonstrations are suboptimal, we can use that to learn a policy uh, for the 20. Okay, so let me take a pause here for a second before I dive into the second half of the talk. But just to summarize, what I just talked about is one of the works that we have been doing, where we can use planning, in this case, classical planning, uh, to help improve the efficiency of reinforcement learning. And the role of planning here was to provide you with demonstrations that then you can use to bootstrap learning of the multi-agent policy. In the next half, I'm going to talk about doing it the opposite direction, where we are going to do classical planning, optimization-based planning, but we're going to mix in learning to improve the robustness of planning. But before I go there, any quick questions I can answer? All right, awesome. So let me jump into that. So I'm going to change gears a little bit. So now instead of an RL-based policy, we are going to have sort of optimization-based policy. And what I mean by optimization is we're going to have some team-level objective function. Let's call it F, and it's going to be in some nice format. And we're given a set of robot strategies, and our goal really is to pick a strategy for each robot, such as so that we maximize the total performance over here. Right? So unlike RL, here we are going to assume that we have sort of additional information so that we can solve this using classical optimization-based planning algorithms. So things, dynamic programming, things sort of convex optimization, sort of those kinds of methods where we have enough structure, enough parametric information given to you that we can solve for the solution using optimization. As a specific example, let's talk about agriculture as the application that I mentioned earlier. So we've been doing work on using air and ground robots for doing data collection in the farm. So the idea is we can collect enough information both from the air as well as the ground, aggregate the information so that we can build maps of what's happening in my farm. To identify which parts of the farm need more fertilization, which parts need more irrigation, and so on and so forth. More abstractly, this is sort of a cooperative planning problem where you have several aerial robots and several ground robots, and you essentially want to plan a path for the aerial and the ground robots so that they can cover the entire environment, collect enough information from all points of interest in the environment. One of the challenges that you face with in a setup like this is your vehicles, especially aerial vehicles, have limited battery capacity. So they can only run for 15 minutes, 20 minutes, 30 minutes, depending on the type of platform that you have. And so you may have to have them land occasionally for you to swap out the batteries or recharge. And so when you're doing your planning, you need to take that into account to ensure that these vehicles don't run out of charge, right? So this is again where we've been looking at coordination, and this is a more explicit form of coordination, where we've been working on using these ground robots essentially as mobile recharging stations for the aerial vehicles. So here the aerial robot is autonomously landing on the ground platform, and the idea is that the ground platform now is, in addition to collecting its own data, can also act as a, a mule for the aerial vehicle. It can carry the aerial vehicle to its next takeoff location so that the aerial vehicle is saving energy. It doesn't have to fly between every pair of points. But if you can also recharge the aerial vehicle along the way, then you sort of are going to increase the operational uptime of your system over here. The question then is, if I have several such aerial vehicles and several such ground vehicles, how do I get them to coordinate with each other to ensure that I'm covering as much area as possible, collecting as much data as possible, while still satisfying this battery capacity constraints that I have. Right? This is a classical optimization problem. If you have all the parameters that are given to you, you can solve this as a planning problem, a multi-agent planning problem with some sort of assignment type constraints in the mix. And we have a series of results for this kind of planning. So here's one example. I won't go over sort of how we actually solve this, but here's an example of what the solution looks like, right? So the blue vehicles are operating on the street network over here. There's two blue vehicles, and the aerial vehicles are flying their own missions. And then every once in a while, you'll see the aerial vehicle come land on the ground platform, recharge, and then sort of go back to its mission over here. And what we are optimizing here is which vehicle should land on which ground robot, where should they land, how often should they land, what sequence in which to visit the points, and so on and so forth. Right? We can sort of model this as either an assignment type problem, which you can solve using integer linear programming type methods, or you can model this as a Markov decision process if you're taking into account uncertainty, and you can solve using sort of classical MDP algorithms. But oftentimes in this setup, even if you can solve the problem using optimization-based method, you still are assuming that there's a lot of parameters that are given to you as input, right? So in this example, I'm still assuming that I'm given the travel time between two locations as input. I'm given the battery capacity, and I know that battery capacity exactly. I know the discharge rate. So how much sort of energy am I going to consume if I travel 1 unit distance? So I'm assuming a lot of parameters are given to me as input. Whereas in reality, a lot of these parameters actually are dependent on the specific context in which your system is operating, right? So if the wind is especially strong on a particular day, your battery capacity is going to be, or your energy consumption is going to be much higher. Sort of if you are operating in dense forest, for example, where your ground vehicle has to avoid going into vegetation, or perhaps has to go over loose gravel, then just the travel time between two locations is going to be sort of longer or shorter than you anticipated, right? So there's a lot of parameters that I assume when I solve these optimization-based planning algorithms that I assume are given, but in reality, they actually depend on context. And so what you would want to do in a setup like this is you would want to learn what these parameters are based on the given context. And then given the learned parameters, you would then want to use your optimization-based algorithms to then find the plan, right? You could also just do pure end-to-end learning. This is what you would do with reinforcement learning, where you would start with data, and then you have some task that you want to do, which is sort of find the routes for these vehicles. And you can sort of plug in a giant neural network in the middle that's mapping directly data to task. As an example, you can think of data as basically being, let's say, the environmental conditions that tell you the amount of rainfall on a given day. That's going to affect the travel time of the ground vehicles. And you throw a giant neural network over here, and at the end you are getting plans for your aerial and ground vehicles. And given enough data, you might be able to learn a policy that tells you, oh, if it rained a lot yesterday, then my ground vehicle should take the route that's going on gravel instead of going through loose soil. But that sort of there's a lot of structure in the problem that we are ignoring if we just do end-to-end learning over here. And then, of course, it's not very efficient. And you also sort of run into issues with explainability because you can't sort of understand exactly what's happening in this neural network over here. A more common way of doing this is to do it in two phases. So the first phase is that if you use your context information, let's say amount of rainfall, to predict the parameters. So in this case, the travel times for all the edges in your graph. And then given the travel time, then you solve an optimization problem using integral linear program or your favorite optimization methods to then get the solution over there. So the standard way of doing this is to do it in two phases. First, predict the parameter and then optimize for your solution. But what we argue, and some recent work that has come out that sort of have made a similar argument, is that even if you have a very good predictor that has a very high predictive accuracy for these parameters, that doesn't necessarily translate into making good decisions at the end over here, right? So I'll show you an example, and it's a bit of a contrived example, but this also holds in more settings over here, right? So let's take a very simple setup. Let's just say there are two routes that I need to choose from for my vehicle. And let's say this is for my ground vehicle. And the context here is the amount of rain, right? So if it's rained a lot, then I should choose one route. Even if it's longer, I should choose that route because perhaps that route is going over concrete, so it's not going to be as affected by rain. Whereas if it's not rained a lot, then I can take a shortcut directly through grass, and it's going to be fine. So you have sort of a plot that shows the travel time for the two routes that I have to choose from as a function of the amount of rain on the x-axis over here, right? And there's a decision point that tells you to the left of this decision point, I should choose the red route. To the right of this, I should choose the blue route over here, right? So if I knew this mapping of the amount of rain to the travel times of each of the routes, I know my decision. I know which one I should choose over here, right? In reality, what you have is you have observations that tell you for this amount of rain, this is how long it took for me to traverse route 1 and route 2. And then what you do is you learn, you essentially fit curves to the two sets of data points that you have, and then make a decision based on it. So for simplicity, I'm just showing the best linear fit. So if I just fit lines for the two curves over here, this is what I end up getting. And this red dashed line is my decision boundary over here. Meaning to the left, I'm going to choose one route. To the right of that, I'm going to choose the other route. Whereas in black dashed line is my optimal decision boundary. In between the two is the part where I'm making the wrong decision over here, right? So I'm correct to the left of this, I'm correct to the right of this. In between, I'm making the wrong decision. Okay. So this is where you are training your prediction using some mean square error loss, and you get this suboptimal decision region over here. On the other hand, if I trained my predictor not using the mean square error loss, so it's not necessarily predicting the best parameters, but I train it based on the decision-oriented loss, it's sort of based on if I choose this route, what's the loss that I would get. Then you will see that this boundary actually shifts a bit to the right, and there's a lower gap. There's a smaller region where I'm making the wrong decision over here, right? So what we argue essentially is instead of doing this in two stages where you first learn the parameters and then solve the decision-making problem, you should instead learn to predict the parameters using the loss that's obtained from the decisions that you are going to make. More specifically, this is the pipeline that we argue that you should use, which is you take in your context information, plug it into a neural network, use that to predict the parameters, solve a decision-making problem, compute the loss over here, and then use that loss to train this neural network instead of using the predicted parameters and then somehow minimizing the mean square error loss with the ground truth parameters. The challenge is I need to make this decision-making module differentiable so that I can take the loss over here and then do a back propagation of this loss to then update the neural network over here, right? So essentially, you can think of your team coordination or optimization-based planning as being another layer in a neural network where I don't need to learn anything for this layer. But if this layer is also differentiable, then I can train this neural network using my downstream task loss instead of just the parameter loss. Meaning that the parameters that I'll end up learning will give me better decisions and not necessarily just better accuracy over here. The challenge, of course, is to make this part differentiable. And in some recent work, we've shown how to make this differentiable for a class of multi-agent optimization problem. So in the interest of time, I won't go over the full details of this, but we've looked at a few versions of sort of combinatorial optimization problems that are typically show up in multi-agent coordination settings, specifically submodular optimization problems. And so the main challenge is, in order to make this optimization differentiable, you sort of need to take the continuous relaxation of the discrete optimization that you have to do. Right? So in a very simple example of this is, let's say you're solving a simple assignment problem. You're just assigning robots to task or robots to route. Your decision variables in this case are binary, 0 and 1. So you're solving a binary optimization problem over here. And there's sort of classical techniques to solve this discrete binary optimization problem. But if we want to make it differentiable, which is what we want to do over here, then one way you can do that is to take the continuous relaxation of the problem, where you make the decision variable to be a continuous sort of real number between 0 and 1, and then sort of find a way of converting back your solution into the binary decisions that you need. And so we sort of show how to do that for a class of optimization problem. And it turns out sort of we can sort of prove a few things in theory. We can show how good of an approximation this is with the continuous relaxation that we are getting. But more importantly, we can actually sort of implement this in practice. And oftentimes, the discrete optimizations that we end up doing can be realized in the form of a neural network. So you can think of this as in the discrete optimization, some of the arc maxes that you have essentially turn into soft maxes that are differentiable. You can sort of show how to realize this in the form of a neural network, right? So we have some sort of interesting results over here. I'll show just one slice of results. So this is for the same setting where you have a bunch of UAVs, bunch of UGVs, and you need to figure out which vehicle should be recharged by which ground vehicle. So you're solving an assignment problem. And what we show here is, if you use this downstream decision-oriented learning instead of the two-stage learning where you first predict and then optimize, we sort of end up performing better than two-stage. It's more efficient over here. The gap decreases if the number of vehicles increases, in some sense because the optimization problem also becomes harder, but you can show that there indeed is a gap. So you're performing at least as well, if not better, than this two-stage optimization. So here, this is an example of how we can use learning to improve planning. And in fact, we have several such sort of things in the pipeline where we want to use differentiable optimization, where you can take classical optimization algorithms that we know how to solve, where we can use our inductive biases, if you will, the structure of the problem, and solve it more directly, exploiting the structure that we have in the problem, without resorting to have assumptions that are unrealistic. So you can still use learning to tell you parameters, but then you don't have to train everything from scratch. You can use your inductive biases to design an optimization algorithm that's still going to preserve the structure that you have in the problem. So that's sort of the second direction that I wanted to talk about, where we can use learning to improve planning. Sort of last piece before I stop here is something that we are sort of quite excited about. And of course, like these days, it's very hard to give an autonomy talk without mentioning LLM even once. So here's my mention of LLM right at the end over here. But of course, there's sort of a lot of interest in using large language models for planning, for learning, for sort of all sorts of things. There's work on using LLMs directly to generate code, or to use LLMs to generate reward signals for reinforcement learning. I think the jury is still out on whether and how much LLMs are useful, but I think it's clear that LLMs are certainly useful in this context. Uh, our argument really is to use LLMs in settings where It acts as a complementary piece to planning and or learning over here, and not necessarily as a substitute for planning and or learning. So just to give you an example of what I mean by that, there's a simple navigation problem. So you have a ground robot that needs to navigate across this room. The classical planning, optimization-based planning problem. You have onboard sensors, you build a map, you come up with a cost map, you find the shortest path using your favorite method, uh, and then you execute that map, and then you sort of replan, you will discover new information along the way. So there's sort of standard planning methods that you can use for uh, but there are scenarios where these methods perhaps don't work as well. So here's an example of this. So this is a setup that we have in the lab. You see a table over here. There's a tablecloth, and if you just look at the map, using the onboard LiDAR over here, you'll actually see that there is no path to go from this side of the table to the other side over here, because the tablecloth looks like an obstacle. And so it ends up sort of showing in the map as an obstacle. And then your planner essentially says, there is no plan for me to go from this side to the other side. And what we argue is this is an example of a scenario where LLMs can be useful because they encode some sort of common sense reasoning. And I'm using common sense as code because I think it's very context dependent when it's useful and when it's not. But in this kind of a scenario where you're essentially breaking glass in case of emergency, your planner is telling you there is no path for you to go from left to right. This is where you can rely on an LLM to then tell you, is there indeed no path for me to go from one side of the table or not, right? And so here, if you then query the LLM using some description of the scene that you are currently in, and you tell the LLM sort of what I'm seeing is sort of, by LLM, I mean sort of foundation models in general. It could be a vision language model as well. What I'm seeing is a table and sort of this and that and so on and so forth. Your LLM may be able to reason that, hey, indeed, in this scenario, actually, this looks like a tablecloth. So you should be able to you should be able to go under the table because this is, and this is not a rigid obstacle in the middle. If you sort of try to go under it, this object would actually sort of let you pass through it, right? And we've sort of done some experiments and we found that this actually works pretty well. So what we have is a framework that uses sort of planning to in its normal form, but then every once in a while, if you have a lot of uncertainty in your planned policy, it then requests feedback from an LLM, which then tells you what to do in those scenarios, and then you sort of translate that feedback back into a set of actions for the agent. So the question that we answer here is, of course, you don't want to use the LLM every single time. So when do you seek feedback? How do you determine that the plan that you have has a lot of uncertainty or is infeasible, and you need to then query the LLM to get additional feedback? How do you get that feedback? So because the language model is going to give you a sequence of actions, but you need to ground those actions with actual actions that the agent can take. And then how do you incorporate that feedback to come up with the exact sequence of actions given the token outputs that they get from and we found that it works pretty well. We have sort of several results where we're comparing with classical planners or sort of without any feedback, and we see not only are we able to navigate in more environments that classical planners fail, we are also able to do it more efficiently in terms of the trajectory. Right. So this is sort of what I wanted to chat about. This is just a slice of some of the work that we've been doing in my group, where we are trying to bring planning and learning together by improving planning using learning and then improving learning using planners. So hopefully you enjoyed the talk. Happy to answer any questions that you have. And thank you again for having me here.
Thank you, Pratap, for the great talk. Let's open the stage for questions. You can either type or just raise your hand and ask directly.
Yeah, one quick question, Professor.
Yeah, go ahead, Pratap.
Yeah, the thing is, I'm very curious to know from your experience over the time, because your group has been working and doing such a fantastic job for such a time. From the sustainability point of view, how did you find the optima? I mean, you had been optimizing. So the energy consumption versus the optimization, what was your observation over the time?
Um, I couldn't fully understand the question. The energy consumption of what?
Say from charge to charge for the robot, or the because you are using say the server
Mhm.
for the data transfer, so everywhere the energy is always used.
Sure.
So from that point of view, have you worked, or have could you correlate with the optimization with respect to the energy consumption over the time?
Sure, yeah. So there's actually a lot of work on characterizing the energy consumption for mobile robots, and oftentimes motion is an order of magnitude higher than any other sources of energy consumption, including compute and communications. And so, if the best bang for buck essentially is to optimize the motion of the vehicles, uh, but for specific type of platforms, like for example this one over here. This is where computation or communication can also be an important factor in energy consumption. There's some work on co-design of systems. So not only are you optimizing the plans, and by plan I mean sort of motion plan as well as communication plan, but you're also optimizing the form factor of the vehicle. Sort of how many motors do you have, how they are configured, and you're optimizing the sensing, like what type of sensor do you need for a specific task and so on. So there's some sort of interesting work on co-design, which I think is relevant, especially for smaller platforms. But for larger platforms, often motion overwhelmingly dominates the power consumption.
Thank you very much.
Yeah.
Thank you, Subrata, for the question. Any other question?
I have a question.
Yeah, go ahead. Sorry.
Hey, Pratap. I have a question about the work where you it was a few slides ago. Um, I think the overall idea was to optimize a neural network, but you had to make the planner differentiable.
Mhm.
Okay. Or the decision making algorithm differentiable. So, um, what would be the difference, or what would be the advantage of using, let's say, the classical decision making algorithms versus just using RL if they're comparable?
Sure. Yeah. So there's a couple of sort of advantages of using classical optimization-based methods over RL. The first is structure. In some cases, there's enough structure in the problem that you really don't need RL over here. And so in terms of efficiency of learning, given that you can use optimization, you don't need lots of data to learn a good sort of or to find the plans over here. So let me give you a very specific example, right? So let's say you have you want to choose a route based on the amount of rain that you have, and the actual relation between the amount of rain and the cost of the route may be a very complicated relation, right? It might sort of be a very sort of high squiggly line over there, right? But the decisions themselves might be very simple. The decisions might themselves just say, if it's rained more than X amount, use route one. If it's rained less than X amount, use route two. Whereas the actual mapping between rain and the cost of a route might be a very complicated function over here. So if you use RL, what you'll end up doing is you'll end up learning a very complicated looking function. So you sort of have a very sort of complicated function like this, and you sort of have to learn a policy, sort of learning a complicated function, and so you have something else. Whereas you could very easily learn a very simple mapping, kind of like this and like this, And so what you're learning are blue curves, which are the straight lines over here, and you don't need a lot of data to learn these straight lines. But the decision that you're going to get by learning these two straight lines versus learning a very complicated function is going to be the same. It's basically saying to the left of this line, use route 1, to the right of this line, use route 2 over here, right? And so what we are arguing here is you don't need to learn this very complicated red function if all you are interested in learning is this decision boundary over here, right? Because ultimately you're just deciding which route should I take. And if you even if you learn these blue curves, which don't look anywhere like the red curves, you're still ending up with the same decision. And so your loss, which is your decision loss, actually is minimal over here, if not zero, right? So what this does is allows you with efficiency, saying that even if your actual relation is very complicated, the the decision surfaces might be much simpler. And by using optimization based methods over here and then using the loss that's coming from these optimization methods, you can learn these simpler surfaces using fewer data, and therefore learn a policy more efficiently. And this is what I mean by inductive biases, because you sort of know in this case what the structure of the problem.
Thank you.
Thank you, Troy, for the question. Any final question for Pratap?
Hi, Prof. Can I ask one question? So,
Yes, go ahead.
in your, in your presentation, you mentioned several times about the scalable and scalability. For example, in your first task, how can you ensure the scalability of your team? How can you make sure, okay, a lot of agents can also work in that kind of scenario or cases?
Sorry, how can we ensure what? I sort of missed that part.
Scalability. For example, there are a lot of agents, for example, 10 or 20 or even 200. How can you make sure your policy will still work?
Yes. Okay. So I guess that maybe I sort of didn't go over a lot of the details over here. So the first idea is, we are still doing decentralized multi-agent RL. So this is still your standard framework that does centralized training and decentralized execution. So you can think of standard decentralized MARL techniques that are being used over here. Each agent, after training, is only relying on its local information to make its decision. So it's scalable in that sense. The challenge that we focus on here is during the training part, the centralized training part. If you like, how do you improve the efficiency or the scalability of the centralized training part? The decentralized execution, because it's decentralized, is sort of, we know it's going to be scalable. But during the centralized training, our idea here with this framework is to do a combination of two things, over here. So a combination of two things over here. So the first term, if you look at line 7, that's your reward function. The first term is your standard reward function over here. And the issue with scalability comes in with this reward function. So for example, if this reward function is sparse, and if I have lots of agents, it will take me a lot of samples to learn any good policy over here, because with a sparse reward function, you really need to explore the state action space to learn a good policy. What the second term ends up doing, which is the term that's coming in from the discriminators that I talked about, that's coming in from the demonstration, this acts almost like a guidance signal. It's sort of giving you an exploration bonus. And so the second term is sort of, you can think of it as giving you a higher reward for certain state actions pairs that are similar to your demonstrations, saying that uh, those are the state action pairs that you should explore before exploring the other state action pairs. And this is where the scalability during the centralized training comes in, because now, if you look at this example that I had over here, if I were doing sort of this pure RL, I'll end up exploring the entire state action space. Whereas with our method, our exploration is mostly focused around the part where we expect the optimal sort of trajectory to be concentrated in, right? So it's sort of guiding your exploration to the part of the state action space that's important over here. And so the reason for scalability, we think, is because if you have a large state action space, which is usually the case if you have many agents and you are planning in the joint state action space, our method ends up focusing the exploration into a narrow part of the state action space where the optimal policy will be concentrated in. Whereas sort of standard methods that don't use what we are doing would have to end up exploring the entire state action space, sort of leading to poor scalability.
Okay, thank you. Thank you so much.
Thanks for the question.
All right. Thank you, everyone, for the questions. And thanks, Pratap, for the great talk. I wish you good luck for the next steps.
All right. Thanks a lot, Jale.
And yeah, and thank you, everyone, for joining, and hope to see you all next week for the next Autonomy Talk. Bye-bye.